Hi, my name is Max Schleich and I would like to present to you LMFAO, which is an engine to compute large batches of aggregate queries. This is joint work with Dan Olteanu. The main motivation behind LMFAO is the observation that many real-world analytics workloads that are computed over multi-relational databases require the computation of large batches of aggregate queries. Typical applications require queries in the order of hundreds or even thousands. And so these are workloads which traditional database management systems were not really designed for. And in fact, we have shown that they don't really perform well for these kind of workloads. So this is why we designed LMFAO specifically for this workload. Given an aggregate batch, LMFAO applies several layers of optimizations on this batch, as depicted by this figure at the bottom of the slide here. And they all are designed to systematically share computation across the aggregates in the batch. In practice, we have shown that we can achieve orders of magnitude performance improvements over state-of-the-art competitors with these optimizations. Before I jump into the actual user interface of the demonstration, I want to give an example using 5 relations and 3 queries that are computed over the join of these relations. The first thing that LMFAO does is it takes the queries and decomposes them into views over the join tree depicted at the bottom of the slide here. And for instance, for query Q1, we decompose the query into one view for each edge in this join tree, and they essentially represent the intermediate computation done as we do a bottom-up traversal of the join tree. The reason why we break it up into views is that when we add additional queries, like query Q2, we can reuse a lot of the computation we have done for Q1. In fact, in this case, we can use all of these intermediate views also to compute query Q2. So we share a lot of computation amongst the queries. As we show in the paper, however, it is not always beneficial to use the same bottom-up traversal for all queries, which is why we allow different queries to follow different traversals over the join tree. This essentially means that each query is assigned to a node in the join tree, and this node becomes the root for this query. In this example, we would assign Q3 to the items node, and then we send an additional view from sales to item instead of items to sales. In addition to reusing views across queries, we also notice that there's a lot of computation is done over the same relations. In this case, for instance, the views for Q1, Q2, and the view from sales to item is computed over the sales relation. And so we group these views together and compute them in one pass over this underlying relation, in which allows us to further share computation across the queries and to share the low-level data access into the relation. Finally, LMFAO generates highly specialized C++ code for each view group that is specialized for the given workload and data. This allows us to choose data structures for each view, inline function calls, perform loop unrolling, etc. And we can also parallelize the computation. Now I will present the actual user interface for this demonstration. And we will choose the k-means clustering application, the retailer dataset for this week. When you click Next, LMFAO generates all the queries that are required for this particular workload, and they are grouped by the node they have been assigned to. So all these queries, for instance, are computed with location as the root. And then you can interact with this join tree to get all the views, for instance, that are computed over location. And if you inspect them further, you will notice that they share a lot of computation. For instance, the join for these two views is exactly the same, which is what we exploit when we compute the view groups. And you can also click on these edges to see which views are computed from location to inventory, for instance. Next, we will group the views, and it creates a dependency graph of all the views, the view groups that are required for this particular workload. And again, you can click on them to see all the different views that are required. And here you see again that there's a lot of shared computation between these views in each view group, such as the join, which require, which we exploit when we compute these aggregates. Now LMFAO has generated the code, and we can choose the file we want to inspect. In this case, we choose view group 4. We can also choose to highlight different code fragments which are of interest. In this case, we want to highlight the output code, which is the code that outputs tuples to these views. And when we scroll down, we will see that there are these red blocks which indicate that this is the code that outputs tuples to these views. Nicely shows that we use different data structures for different views. For instance, here we use hash maps because we need to worry about deduplication for these two views that we generate here. But when we look at the view generated for view number 32, we know that the tuples are enumerated in order, so we don't need to worry about duplicates. And so we can just append each tuple at the back to an array, and that makes this computation much more efficient than using hash maps throughout. Finally, we will execute the code to run the application. Now the code executed, and by default, LMFAO computes 10 clusters, and we compute the clusters using the RK-means or relational k-means algorithm, which is a novel clustering algorithm we recently presented at AI Stats. The algorithm works on a small approximation of the data set called the core set, and in our case, this core set is only 2% of the original join result. In the AI Stats paper, we show that the algorithm with the LMFAO optimizations can lead to an order of magnitude speed up over the state-of-the-art competitors with very minimal approximation error. On this note, I end the presentation. Thank you very much for listening. If you would like to learn more, please get in touch or check out our website.